Good evening. My name is Aida Milena Chavarría Garcia, professors at the Universidad Escuela Colombiana de Ingeniería Julio Garavito, located in the city of Bogotá, Colombia. The work presented in this poster is entitled Influence of Silicon Carbide Reinforcement Amount of AIC 316 on Electrochemical Response and Corrosion Resistance of a Composite Material, and was carried out jointly with the undergraduate student in mechanical engineering, Paula Alejandra Contreras, the professors David Blanco and Lorena Cárdenas, also from the same institution, and with the collaboration of the professor Francisco Bolívar from the Universidad de Antioquia in Medellín, Colombia. The object of this work was the fabrication of a metal matrix composite material by powder metallurgy technique, which consisted in an AIC 316 steel matrix with a reinforcement of silicon carbide particles in amounts of 0, 2, 4, 6, and 8% in order to improve its corrosion behavior. The procedure starts with the homogeneous mixing of the steel powder with a silicon carbide particles in a planetary ball mill with a ball to load ratio of 3 to 1, operate for 30 minutes at 90 RPM, varying the reinforcement content as indicated above. The uniaxial compactation process was then carried out, adding a zinc stearato lubricant to the powder mixture and applying a load of 700 megapascals. Once the compactation was completed, a sintering process was carried out at 1250 Celsius degree for 30 minutes. Once the samples were obtained, morphology evaluation were carried out by electron microscopic porosity estimation and the electrochemical and corrosion resistance evaluation by electrochemical impedance and potentiodynamic polarization, respectively. In the results, we can observe the microstructures of the steel samples and their different additions. For the AIC 316 sample, a microstructure of fine grains and oxide roots is observed, and very noticeable microcracks throughout the surface after the sintering process. In the case of the sample with a 2% silicon carbide, oxidized areas, porous, and areas that formed nicks were observed, showing the formation of a micrograins. On the other hand, the sample with a 4% of reinforcements showed a compact microstructure after the sintering process with a good compatibilization at the interface of the matrix and the reinforcement. The samples with 6 and 8% shows area where the reinforcement is not homogeneously distributed and the matrix is present on the surface of the materials, showing that the reinforcement was not compatible with the matrix at the interface. During the evaluation of the porosity, the 4% silicon carbide samples showed the lowest value, even than the steel. On the other hand, the 6% reinforcement showed the highest values surpassing the steel. For the electrochemical results, the impedance curves indicate that the 4% silicon carbide sample, after 7 days of immersion in sodium chloride electrolyte at 3.5% by weight, presents the highest capacity arc starting its decrease at 300 ohms, which indicates a higher resistance to deformation of the electrolyte through the microstructure of the material. In this order, the 2% silicon carbide content showed a drop in the capacity arc around 150 ohms. These two materials are the ones that presented higher capacity arcs than the sample without reinforcements, which falls at 90 ohms, indicating less electrochemical activity given the microstructure microstructural characteristics. On the other hand, the 6 and 8% silicon carbide reinforcement showing high electrochemical activity and thus the small capacity arcs with a ohmic drops of 50 and 25 ohms respectively. The materials then show the conformation of parallel equivalent circuit where two times constants are present with the resistance offered by the seal and the resistance present by the acicular silicon carbide particles. Therefore, the electrochemical behavior is dominated by the permeation capacity of the electrolyte into the materials through the pores left after the sintering process. In the potentiodynamic polarization results, the sample with a 4% reinforcement shows a more electropositive potential than the rest of the samples, followed by the 2% reinforcement and the still sample. This indicates that the 4% sample offers the best corrosion protection. These results are consistent with those obtained by electrochemical impedance and porosity evaluation. As for the corrosion currents, the sample with a 2% reforming show with the lowest current density, indicating that this material is efficient against corrosion due to the potential present and allows less current to the pass through the system, reducing the capacity of the material to trigger corrosion process, presenting greater resistance to polarization. As for the material with a reformance for 6%, it presents the highest corrosion current since there was a diffusion of chromium to the surface of the materials, as can be seen in EDX mapping of the image, which increases the conductivity of this material and thus increasing its electrochemical activity. As a conclusion, the fabrication and synthesis of an IIC 316 steel matrix composite material with a silicon carbide particle reinforcement of 0, 2, 4, 6, and 8% was performed. The microstructure of the different materials was evaluated, finding that the sample with a 4% reinforcement has a compact and dense microstructure after the sintering process, and 8% with a structure with a reinforcement particle that were not compatible with the metallic particle matrix at the interface where is no nick formation. Due to the high degree of the densification of the sample with a 4% reinforcement, it showed the lowest electrochemical activity and the highest corrosion protection. The sample with a 6% reinforcement showed a high electrochemical activity and low corrosion resistance due to its low potential and high current density and the diffusional process of chromium towards the surface of the materials. In the end, the electrochemical behavior and corrosion resistance is defined by the degree of the densification of the material after the sintering process and diffusional process of conductive allowing elements toward the surface of the materials in initial contact with the electrolyte, indicating that the amount of ceramic reinforcement does not define the electrochemical activity and corrosion resistance. Thank you so much for your attention.